Okay, so let us next start chapter 3, Trigonometric Functions. Let us recall the definitions of trigonometric ratios that we learned in school when trigonometry was first introduced to us. And for that, we have to go back to the very notion of angles. What is an angle? Let's see that first. So, an angle is a geometric figure which consists of two rays. That means we have to first of all see what a ray is. A ray, roughly speaking, is half of a line. A straight line, we normally know it doesn't end on either side. Say you consider a straight line like this. So this is a straight line. To indicate the fact that it doesn't end on this side as well as on this side, we normally use arrowheads like this. Okay, these arrowheads indicate that the line continues on either side without any end. That's our usual straight line from Euclidean geometry. Now, a ray is obtained from such a line by choosing any point on it and then considering only one half. From this point, either you take this half or from this point you take that half. And if you remove one half, whatever you are left with, that's a ray. Okay. And such a ray has this distinguished point. There are other points, of course, there are infinitely many points on this ray. But this distinguished point is called the initial point. Say you can name this O and say OA is the ray, where you must understand that here A is not a point on this figure, but it just simply indicates that the ray is going from O towards A, whatever that means. Now, an angle consists of two rays like this, which have the same initial point. So let's draw one such figure. Say this is one ray. It's not necessary to draw one of the rays horizontally. No, that's not necessary. You can just take any ray. So this is one ray whose initial point is this O, and it goes indefinitely in that direction, OA. And you take another ray like this, which goes in some other direction or may in fact go in the same direction, in which case we are considering the same ray in place of two rays. That is one of the cases, but in general you have like this. Say this is OB. So the rays OA and OB have the same initial point O. When that happens, this figure is called an angle. The figure itself is called an angle. So the definition of an angle is just this, that an angle is formed by two rays having the same initial point, or an angle is the figure formed by two rays having the same initial point. Now, such angles are plane angles. They are called plane angles because the rays that form them lie in a single plane. But there are some angles which are formed by two intersecting planes as well. They are called dihedral angles. We won't need them. Okay. There are other kinds of angles also. We are only going to need plane angles. two curves can also intersect like this. They also make an angle, but those are not needed for us. So we are considering a plane angle. Now here's the thing. Say you take a plane angle. For convenience, we take one of the rays horizontal. This is merely a convenience for us, okay, because this is how we normally have seen things in lower standards when we were introduced when the trigonometric ratios were introduced to us, this is how things looked. So that's why I have taken one of the rays of the angle horizontally, and the other ray is in whatever manner it is. Alright. Now, before I say what we can do with this, there are further names that have been given to the individual components of an angle. This common initial point is also called the vertex of the angle, vertex of this figure, which we are calling an angle. And the individual rays are called sides of the angle. So this is one side, this is another side. So that means one of the two sides we have drawn here horizontally, and the other side looks like that. Now you know that normally when we say angle, we have a numerical value like this, say 42 degrees, 31 degree, or 90 degree. Then what am I saying here? See, these are geometric angles, plane angles, and each one is associated with a numerical value, which is the magnitude of the angle or its angular measure. I mean, as a geometric figure, we have an angle, a plane angle, but the plane angle comes with numerical values. Those angular measures are also called angles. Okay. In the context of trigonometry, when we consider an angle, we usually do not simply mean this figure itself, but the figure with its angular measure. Actually, there are two angular measures that an angle can be associated with. One of them is this, and the other one is this. So here we are considering this one. In other words, we do have the geometric figure which we are calling angle here, but along with that we also have that angular measure, say theta, and let us take the unit to be degree. We already know what degree unit is. Alright, now what we do, we take any point on the OB side and we draw a perpendicular from that point on the OA side. Okay, and let's give these points some name also. So let me call this B1, and the foot of this perpendicular, let me call it A1. And so you can see that we have a plane triangle, an ordinary triangle in the plane here, whose three sides are this, this, and this. These sides will have some lengths. Let me call the base side length B, and this side length, let me call it H. You can call them anything you want, and let me say this is P, or this may look, I have written H here with height in mind. However, you already know the names of these sides. With respect to this angle, this side is called the base or adjacent side. You already have learned these things. This side is called opposite or altitude, or sometimes also called height, and this one is invariably called the hypotenuse. So let me just keep that in mind and instead call this P perpendicular and this one H. These are the lengths. Okay. Now once this is given to us, we are ready to go back to the definitions of sine theta, cos theta, those things. So let's just recall those definitions. So what we are doing here is nothing new. We already have seen these things. We are just recalling the things. So what is sine theta? Instead of again and again writing theta degree, let's assume that the unit is in degree. The unit is degrees. This is the P side, that side length P divided by the length of the hypotenuse. Cos theta is base divided by the length of the hypotenuse. Then tan theta is P divided by B. Okay, and then next come the reciprocals of these things. The reciprocal of this sine theta is cosecant theta. Some people write COSEC, and the modern notation is simply CSC. Okay. This is the reciprocal of sine theta, that is H divided by P. The reciprocal of cos theta is secant theta, SEC. So that is H divided by B. And the reciprocal of tan theta, the tangent ratio, is cotangent, which is B divided by B. Okay, so these are all the familiar things that we already know. Fine. But now you note carefully that the angular measure of this angle is less than 90 degree and greater than 0. Because that's what it is. No, it's not 0. The side OB is not coinciding with the side OA. Also, it's not a right angle. Its angular measure is not 90 degree. Had that been the case, we would have this. Okay, that would have been OB. And such angles are called acute angles. So we are in fact considering acute angle here. Now, will anything change if I change this point B on the side OB, I mean B1? Nothing actually will change. You can see that I chose this B1 arbitrarily on OB. I actually took any point on OB as B1, except of course the vertex. Any point other than the vertex. Nothing changes if I change B1. That's because, say I take another choice. If I instead take this, say, this is say B2, and I similarly drop a perpendicular from D2 on the side OA. Let this new foot of the perpendicular be A2. The original length, I mean the old length B of the base is there, the old length P of this altitude is there, and H is there. Okay. So now we have a new altitude or a new perpendicular. Let me call this P prime. A new base OA2. Let me call this B prime. And a new hypotenuse, smaller one, let me call this H prime. If you instead use this smaller triangle, but note that just like the larger triangle, this triangle also has that same angular measure because the angle hasn't changed. See, do you see this? The angle hasn't changed, only this altitude has changed because we have chosen another point B2. Will you get the same ratios? Yes. For example, if using this smaller angle, the smaller triangle, I write sine theta, it will now be P prime divided by H prime. Of course, P prime is smaller than P, H prime is smaller than H, but because these two triangles OA1B1 and OA2B2 are similar, so the corresponding sides are in the same ratio. So we end up getting the same ratio, although these individual numbers may be different. Okay, so that's how we justify the fact that it is the angle that matters, not the side lengths, because we are not considering side lengths but their ratios, which do not change. Fine. Now, these definitions, the way we see them here, they work only for an acute angle, not also for 0 degree or 90 degree. So what do we do? What did we do actually for 0 degree and 90 degree? Do you remember what we did? You cannot, you can draw a 0 degree angle. For that you have to take OB also as OA. That, however, we won't do. Instead, what we do, we take a different OB, an OB which is not exactly OA but is trying to become OA. Or to put it more simply, this angle theta is becoming smaller and smaller and smaller, like this. At any stage it looks like this. Okay. So here also you can arbitrarily choose a point and drop a perpendicular from that point on the OA side. Again, this is your H, this is not H, this is P, B, and this is your H. So sine theta is still P divided by H. Now, as the angle gets smaller and smaller, P becomes smaller and smaller. So, it is reasonable to define, because of this fact, this observation, it's reasonable to define sine 0 degree to be equal to 0. This is only a definition, and this definition does not depend on right angle triangles. Because if these two sides coincide, we do not have a triangle. Or yes, you can stretch things even to that case and still drop a perpendicular from any such point on the side OB, but then the perpendicular has 0 length. In that sense also you can say that sine theta should be 0. However, these definitions only work for acute angles. And in this case, the triangle you will obtain in that case where you have 0 degree will be a degenerate triangle having no area at all. It doesn't even look like a triangle, it will look like a line segment. But anyway, it is reasonable to define sine 0 degree to be equal to 0. Similarly, what about cos 0 degree? Cos 0 is, let me just for the sake of understanding, let me write it as b divided by h. Now from here we can clearly see that the hypotenuse length is greater than the base length. But you can imagine that as the angle gets smaller and smaller, this difference itself becomes smaller and smaller. H tends to be equal to B. H tends towards B. And that is why it's reasonable to define cos 0 degree to be 1. In a similar manner, if you draw that other thing where this OB is trying to become perpendicular to OA, from such a figure, you can consider things and you will ultimately convince yourself that sin 90 degree should be defined to be 1 and cos 90 degree should be defined to be equal to 0. Now from these definitions one can clearly see that sin theta divided by cos theta is tan theta. Even if that is not a definition of tan theta, but it's a relation that is a consequence of these definitions. If you define sin theta and cos theta and tan theta like that, then it turns out that tan theta is sin divided by cos. Now using that relation, you can extend all the other ratios to these two angle values. Okay, for example, tan 0 is going to be 0, cot 0 will not be defined. So such problems of not being defined which are not present for acute angle will be present here, and we already know those things. Okay, fine. So these were all the things that we already knew. Okay, we already know these things. Okay. Now let's think of other values of angles. In our definition of a geometric angle, we already have angular measures greater than 90 degree, of course, for example 120 degree. Now the problem is that these definitions do not say anything about this. For example, this value is not covered by this definition. It lies outside of the scope of this definition. So sin 120 degree, for example, right now for us is meaningless. It does not even have a meaning. We only know sin theta when theta is an acute angle or 0 degree or 90 degree. The moment we go beyond 90 degree, we don't really know what these things mean. We do not have any meaning yet, and we are also not clear what it should mean. I mean, you can draw the angles. For example, let me just draw roughly a 120 degree angle. And try to force the existing definition in that case. Let me just see what happens. So this is my one side of the angle and this is the other side. This is the 120 degree. It may not be accurate, okay, because I have simply just drawn it like that. But you can imagine that 120 will roughly look like this. Now if you choose a point on B and drop a perpendicular from B to the side OA, you cannot actually do that. Do you know why? Because OA is not a straight line. It's not exactly a straight line. OA is only a ray. So of course, you can extend it to this side, but then on the extended portion you can drop a perpendicular, fine. but that is not the same as dropping a perpendicular from this point to OA. No, you cannot do that. As a result, if you now consider this right angle triangle, then you are, and then you say similarly try to define the trigonometric ratios, that will not work, because in that case you are essentially considering the ratios for the angle 60 degree, not 120 degree. The existing definition works only when the angle is an acute angle, and at most when it's 90, but not beyond that. So what do we do? Are we going to be ultimately unable to assign any meaning to these values where the angles exceed 90 degree? Now we want to say that we can have values here also, in these cases also. Or in other words, we want to extend the existing definition so that these other larger angles are also covered. Now, how large can these angles be? If you think of angles, say this is your, I am not drawing x and y axis, okay. These are positions of the sides of our angle. Say one side is this ray OA and the other side is OB, which is changing. If the angle is like this, then it's an acute angle, for which we already know the trigonometric ratios. Even for the right angle also we know the trigonometric ratios. But for obtuse angles we do not know. Say our B is in this position. Then for such angles we do not know what the trigonometric ratios are. We need to define those things. For straight angle also we do not know 180 degree, or even going beyond that, reflex angles. And in this way, if you continue increasing the angle, the largest angle you can get is the complete revolution, 360 degree. Okay, so this region of our angles are not covered by the existing definition. So we want to extend our existing definition so that these angles are also covered. But we do not want to do exactly just that. We want to do even more than that, much more. And because of that, we are going to change the definition of angle itself. These geometric angles, which are formed by two rays, now are going to be changed, and we are going to extend the meaning of angle itself by changing things from static to dynamic. A geometric angle is a static geometric figure, right, where nothing is actually changing. You have two rays having the same initial point, which is the vertex of the angle, and that's it. And because of that, the largest angular measure an angle can have is 360 degree. But now we are going to associate angles with a physical process, the process of rotation. Let's see how this can be done. Imagine that one of the sides of our angle is fixed. I mean, now also we have angle which consists of two rays, but one of the sides which we are pretty consistently drawing horizontally is thought to be fixed, which we will call the initial side, and the other side should be interpreted as going through a rotation, and that rotation starts from this position. So it's like a process where the ray OB is rotating, but with respect to what? Rotating about the point O, because the initial point of OB and the initial point of OA, which is O, must remain so. Okay, that should not change. But OB initially starts in this position. So OB at the initial stage coincides with the ray OA, but then it undergoes a rotation. Say that rotation has taken OB to this position finally, and then it stops. So the rotation has started from here, and OB has suffered this rotation, and now this is its final position. In this sense, this is called the terminal side. Okay, it is where the rotation ends. Since the rotation has started from OA, there is a sense in this rotation where OB has gone from here to here. So there is an arrowhead. Actually, I should not have put arrowhead here. Out of habit, I have done that, but for a geometric angle, we do not normally put arrowheads. Okay, it's just the angular measure. There is no sense in which, because these are not associated with rotations. Now only we are talking about rotations. So there is a sense in which this rotation has happened, and this sense is anti-clockwise, this particular one. Here the rotation is opposite to how the clock hands rotate. The clock hands rotate like this, here the rotation is like this. Anti-clockwise, or sometimes we also say counter-clockwise. Instead of this, if you have a clockwise rotation, that is also possible. So this is your initial side, and say the rotating side has gone through a rotation like this, of this much, and this is its final position. So this is the initial side, and this is the terminal side. Here the rotation is clockwise, so this is opposite to this, two senses in which rotation can happen. Fine. At first it seems like we are not really doing anything new, because what's the big deal? We have associated such a geometric angle with the process of rotation. Will it give us anything new? Let's see. You see, previously the largest angle we could have had, angular measure for a geometric angle is 360 degree. That thing corresponds also to a rotation, and that rotation is one complete revolution. So what happens here is this. This is your initial line OA, and the rotating line has started the way it starts here. It has suffered an anti-clockwise rotation like this, it has made one complete revolution and has come back to that same position. So you can write B also here if you want, and the rotation is like this, 360. I mean, if you are writing the angular measure, then this is 360 angle. But because we are talking about rotation, we need not stop here. We can continue. And we can have, say, an angle like this. This is as usual the initial side, that is the terminal side, but the rotation involved here is not merely this, but this. That can happen. This rotating ray has gone through one complete revolution and then another rotation. That can happen. Okay, that is also a legitimate rotation. So the angular measure involved with this rotation obviously will be greater than 360 degree. In fact, it will be how much? 360 plus 90, 450 degree. So initially 450 degree was meaningless for us because such an angular measure did not correspond to any geometric angle, but with the process of rotation that makes sense. And you can now see that in this way you can in fact think of an angle or a rotation, okay, for the time being let's not call this thing an angle but a rotation. You can imagine a rotation whose angular measure is as large as you want. You can now think of 1000 degree, 1 million degree, 1 billion degree, 1 trillion degree. You can imagine such rotations many, many times. What is more, these are all anti-clockwise or counterclockwise rotations whose measures are by convention taken to be positive. But to account for the other sense also, we can introduce negative measure. It is simply a convention. It's like you measure temperature. No? So in some scale, say in Celsius scale, there is a 0 degree Celsius temperature, but temperatures can go below that also. So conveniently we assign negative values to those temperatures. It is somewhat like that. To clockwise rotations, we assign negative angular measures. So in this way, by extending the definition of angle, we won't exactly call this thing a geometric angle, but it is a rotation with which we have assigned an angular measurement. That angular measurement can have any value, any positive real number as value. It can be 0 also, or any negative real number as value. For example, this particular one will be some minus, say, minus 60 degree. Okay, that will look like this roughly, because the sense in which the rotation happens here, that is the clockwise sense, and that's considered to be negative. So we have successfully via rotation extended this angular measure from the narrow range of 0 to 360 to R, the set of real numbers. Okay, and we are going to extend the existing trigonometric functions which work only for angular measures between 0 and 90 to all these angles. But how? That's the question. How are we going to do this actually? Now, before we go to those things though, let us also talk about the two units of angle, the two units of angular measure that we are familiar with. There are others also, but these two are the most used, most frequently they appear. One of them, of course, is the degree measure, and the other one is the radian measure. An even more fundamental measure is the number of revolutions. Now we can say number of revolutions because it's revolutions we are talking about. And in terms of that, we can define what 1 degree means. Say you have your initial ray here, and we agree to assign angular measure of 360 degrees to this rotation, 1 revolution in the anti-clockwise sense or counterclockwise sense. In the revolution unit, the angular measure is 1 revolution. But in degree unit, let's agree that this is 360 degree. This rotation can be divided into 360 equal parts. One part of that will then correspond to 1 degree. That's what 1 degree is. It's 1/360th part of a complete revolution. That's the definition of 1 degree. 1 degree further is subdivided into 60 equal parts. One such part is called a minute and is written like this, 1 prime. 1 minute further is similarly divided into 60 equal parts, and one such part is called a second, denoted like this, 1 double prime. I am not writing these things systematically because these are things you already have seen, okay, in lower standards. So that is your degree measure. But what is radian measure? For radian measure though, we are going to need a circle. Say you have a circle like this. The circle has some center, and now there is an angle. Whose vertex, you can think of this as a geometric angle, but because we have decided to extend things using rotation, so it's better we think in terms of rotation. Okay, so this is your initial side of the rotation. So essentially we are now considering rotations, not exactly angles, not exactly geometric angles, but still the kind of rotation we are considering, those rotations also have an initial side and a terminal side. The terminal side rotates and comes to a final position, and that determines the rotation, and that also comes with a corresponding angular measure, which is a number. We already have seen 2 units, one of them is revolution and the other one is degree. Now we are going to see radian. This is one such rotation. Okay. Now say the radius of this circle is r, some positive real number. Note carefully that I am not taking r equal to 1. R is some positive real number. It may be 1, it may be greater than 1, it may be less than 1. We are coming to that afterwards. Now, this angle whose vertex coincides with the center of the circle determines an arc on the circle. This arc, say this is A prime, this is B prime. That circular arc A prime, B prime. That circular arc obviously will have some length. Let the length be S. Then the radian measure of the angle A prime O B prime. We usually write an angle like this, is defined to be S divided by R. If you divide that arc length by the radius, you will get a number. That number is the radian measure of the angle, of this angle. Now again, one question arises. If you change, because you see here I have taken a circle of radius r, but I haven't said what r is. We only know that r is positive. If someone chooses some other r, will this change? Say one choosing another r means considering another circle. Say I consider a smaller circle. Here I have another value of r which is smaller, r prime. And you can clearly see that this new circular arc on this smaller circle that the angle makes has a smaller length S prime. So if I instead use this circle, then according to that same definition, the radian measure of this same angle should be S prime divided by R prime. Is there a possibility that these two will be different? No, actually they won't be different, and this comes from the similarity of these circular sectors. Just like triangles are similar, circular sectors can also be similar. And just like similar triangles, the corresponding sides of a circular sector are in the same ratio. One of them, of course, is not a straight line, it's a circular arc. But that same ratio thing continues to be true here. So, using a different circle doesn't make any difference. We end up having the same value. And that's why you can use any circle. Now, normally what we do, we take r equal to 1. Or in other words, we consider a unit circle. So, you can imagine that in a unit circle, what will be 1 radian? Let's just see that, because that's how it is usually introduced. Instead of taking a circle of arbitrary radius, let's take a unit circle. So this is a unit circle. And say you again have an angle like this. Now the radius is 1. So if you want this angle to have 1 radian measure, what should this S be? Naturally, S should also be 1, because S divided by 1 should be equal to 1 radian. Okay. So S should be equal to 1. That's why normally to define 1 radian, what we do, we take a unit circle and then in that circle we take an angle whose vertex coincides with the center of the circle, such that this arc that the angle makes on the circle is of unit length. When that happens, then the angle has radian measure 1 radian. So this is your radian. But there may be a slight confusion about these things. That's because it may seem like that we should always take our angle within 360 degree, but that's not necessary. This angle, though it looks like a geometric angle because we haven't said in what sense it's going or those things, it's actually related to rotation. It's not exactly it's not a geometric angle, but it's in fact a rotation where the initial line is this and the terminal line is rotating. So you can have those types of angles here also, angular measures, where say we have 450 degree. But in that case, what type of value will you have in place of S? R of course is not going to change, and for simplicity one can take R equal to 1, or one can fix R to be something, but then that does not change. Let's take one example. Say you have a circle of radius 1, say a unit circle. Okay. Now there is an angle which is like this. The rotation of course starts here. Let me also call it OA. The rotation starts here but then makes one complete revolution, two complete revolutions, three complete revolutions. What should the corresponding value be here? I mean, you have already made one complete revolution, but then once more you have made a revolution and then once more. One complete revolution corresponds to the entire length of the circle itself, which is its circumference. Because the circle has radius 1, its circumference will be 2 pi times 1 or 2 pi. That corresponds, that length on the circle of the circular arc corresponds to one revolution. But we have made 3 revolutions like this. So that means in place of S you now have 3 times 2 pi. The total amount of distance covered by the moving point, because this terminal ray always is intersecting the circle at a point. As the ray is rotating, so is the point. So it's the distance traveled by the point on the circle. That's what this numerator is. If we simply say arc length, it seems like we cannot go beyond one revolution. In a sense that is true if you are simply thinking of geometry. But if you think of this physical process of rotation, then it becomes more clear. This S is not exactly arc length, but the distance traveled by that point of intersection of the terminal ray and the circle along the circle as the rotation happens. Total distance traveled. That is why in this case this is 6 pi and the radius is 1. So the radian measure of this rotation or this angle, sometimes we instead of saying rotation we say angle, okay. The radian measure of this angle is 6 pi divided by 1 or 6 pi radian. Had this happened in the clockwise direction, we would get minus 6 pi radian. That's it. That's the radian measure. All the confusions that most of us have with the radian measure can be eliminated by thinking of that point which is rotating along the circle, as the terminal ray is also rotating either like this counterclockwise or in the clockwise sense. This is the distance travelled by that point divided by radius. That's the radian measure of the corresponding rotation. And finally means I am not going to stretch this anymore. Just one more thing. The relationship between degree and radian measure. When we have two units to measure the same thing, we have conversion relations. So we already know this relation, but how does it come? How does that relation originate? So again, for the sake of simplicity, by now you understand very clearly that taking a unit circle is merely a convenience, nothing else. You can take a circle of any radius. So again we are going to take a unit circle, say, and we have our initial, this is not a circle, it looks like an ellipse, but you understand that freehand drawing is just like this. Okay, so we have our initial line. Now say the rotation is one complete revolution. And because the circle is the unit circle, I should not say the unit circle, but a unit circle, a circle of radius 1. So we have 1 here. So the point goes like this and travels around the circle once and comes back to its initial position. And in doing so, it traverses an arc length 2 pi, because that's the circumference of the circle. So the angular measure of this rotation in radian is 2 pi radian. Sometimes we write RAD, okay, simply RAD. But that same rotation in degree measure is 360. So 2 pi radian is equal to 360. Or if you simplify things, you get pi radian equal to 180 degree. So this is the relation using which you can convert the angular measure of some angular sum rotation from one unit to the other. If you are given the angular measure of a rotation in degrees, say theta degree, to turn it into radian, you multiply by pi divided by 180. Because from this relation, you can understand why we are multiplying theta by pi over 180 to turn it into radian. Similarly, if you have theta radian, to turn that into degrees, you multiply the angle by 180 divided by pi. It will be this degree. If you find this somewhat difficult to remember, which one is to be taken with which one, you remember it like this. If you have degree and you want to turn it into radian, then the degree should get less preference because we are turning things into radian. So the degree unit, this is the degree thing, right? The number which comes with degree in that relation, that is below the more important one, pi. So for radian, pi is above 180. For degree, 180 is above pi. That way you can remember. So some problems will come in your exam where one angle will be given, you have to change the unit. So you have to do this. Is there anything else that I would like to say about these things today in this video? Let me just see if I have missed something. Oh yes, okay, yes. Yeah, there is one more thing. It's nothing new, it's related to these things, but we just want to see one thing separately. We just want to make an observation. Say you have a circle, right? And there is an angle like this. Say the angle has angular measure theta radian, and say the radius of the circle is r, and the arc length here is s. Then theta is equal to s divided by r. You have to remember this relation. Note that this relation actually is a definition. It is not coming from something else. This is what theta radian means. So using this relation, there will be some problems. Say theta and s are given, you have to find r, but that is rarely asked. Usually you will be given directly, say s and r, you will have to find theta. Or say you will be given theta and r, you will have to find s. Okay, so this you need to remember, and this is also something you need to remember. And this is not true. If theta is in degree, then this is not true, because this happens only when theta is in radian, because that's what theta radian means. For degree, if you want to write such a relation, first you have to turn that into radian and then only you can write. So if you have theta degree angle, this is not equal to s over r, but this is equal to s over r, because first you turn theta into radian, you multiply by pi over 180. Once it gets turned into radian, then this relation continues to be true. Okay, so with this we are going to stop tonight. In the next video, we will see how we can extend, because that job is still there, okay, we haven't done that. How we can extend the existing trigonometric ratios from that narrow range of 0, 90 to all these values. Okay, that definition is going to be geometric, but it's a very nice definition. You will see that in spite of extending the angles themselves so wildly, I mean previously we had only 0 and 90. We had other angles also, but we did not have trigonometric ratios for those angles. But now we have any real number as angle, positive, negative, anything. So that means the extensions are also going to be really wild in the sense that now you can put many angles in the trigonometric ratios. Sine minus 1000 degree. In spite of all this wildness, those relations that we know very well, say sine squared theta plus cos squared theta equal to 1, they are continue to be true even in this general setup. Okay, so with that I am ending. And what do we have tomorrow? Man, this heat wave. There is a severe heat wave that's passing. It will persist, I think, for 3 or 4 days. It's just too much. But anyway, tomorrow we have linear algebra. So, and we are solving problems, right? So there will be a community post. So see you tomorrow with that. Until then, this is me, Lucifer, from A Mathematical Room. Have a nice night.